we continue our discussion on conservation of energy by looking at another type of potential energy, this time elastic potential energy, also known as the potential energy stored in a spring. So suppose for a minute that I've got some wall, and I've got a spring attached to that wall, and attached to the other end of the spring is some mass. Now, let's say we've got some equilibrium distance that spring likes to be stretched. Let's say this is our equilibrium distance. And I grab the mass and I pull it over here so that I have stretched the spring by some amount that we will call x. How much potential energy is going to be stored in that system? Well, the elastic potential energy, or also called the spring energy for short, is going to be given by 1/2 K, where K is the stiffness of the spring. 1/2 the stiffness of the spring times how far I've stretched it squared. Now you might ask, why is it how far I've stretched it squared? Well, if I've given it a positive displacement, x might give me a positive number. If I give it a negative displacement, x might give me a negative number. But I should still get more energy if I'm displacing the amount either in the positive direction or negative direction. So we end up squaring that x, so that no matter whether I'm stretching the spring or compressing it, that's still giving potential energy. Because if I compress the spring and let it go, it has the potential to give me kinetic energy. If I stretch the spring and let it go, it's going to still give me kinetic energy. So we square the x so that the positive and negative signs don't matter. Let's do an example explaining exactly how you should solve problems using conservation of energy. One of the things that we're going to do this is look at before and after pictures. So here, I am going to call this picture 1. What I have, I've got a hole in the ground, and in that hole I have a spring that I've put a ball on top of. I've compressed that spring, and I've compressed it by some amount, x. When I let that ball go, it's going to get launched upward, and in picture 2, the ball is just going to be reaching the spring's equilibrium position, which we're going to say is at the top of that hole in the ground. And then the ball is going to pop up. So in picture 3, I'm going to say it reaches some maximum height. So I've got a spring in a hole in the ground. I compress it and put a ball on top. The spring expands back to its equilibrium position. And eventually, the ball reaches a certain height. I've got 3 pictures. I want to consider what's going on in the energy of each picture. Let's start with picture 1. Well, the most obvious type of energy I have is spring potential energy, because I've compressed my spring. So if I look at the spring potential energy, it should be 1/2 K times x squared. My spring potential energy, easy to calculate. I've compressed it by an amount x. Actually negative x since it's going down, so my spring energy will be 1/2 kx squared. What about my kinetic energy? Well, right when it's at the bottom there, it's not moving. So my kinetic energy, which is normally 1/2 mv squared, since my v is 0, I will just write that as 0. Kinetic energy is always 1/2 mv squared. If v is 0, then I'll get 0 kinetic energy. Now you might think that you have no gravitational potential energy because right now we're at the bottom. We're lower than the ground level. However, our height is not 0. Our height is actually negative x. So if the gravitational potential energy is the mass times the gravitational acceleration times the height of the object, I would have to plug in the height of the object here. In this case, that would be mg times negative x. So I'll say it's x with a negative sign in front. So I have a little bit less energy because we're starting lower than the ground level. I actually have negative gravitational potential energy. That's not a problem. Energy can be negative. We can deal with that. But the total energy is just going to be the sum of these three things. So if I look at E total, that would be 0 minus mgx plus 1/2 kx squared. Let's keep building our chart. Let's look at picture number 2 now. Well, in picture number 2, my spring has expanded. We've called the ground the equilibrium position. So that would mean that the spring potential energy, since my spring is no longer compressed, that's going to be 0. Similarly, the gravitational potential energy, if I'm at the ground, we've defined ground to be the point we're measuring distance relative to. My gravitational potential energy has also got to be 0 because gravitational potential energy depends on the height. If the height is 0, I've got to get 0 gravitational potential energy. Kinetic energy, now the ball is moving upward, so it does have some kinetic energy here. I'm going to call that kinetic energy 1/2 the mass of the ball times the velocity squared, and I'm going to call it v2 squared since it's moving up. So let's see, the total energy in this case would be 1/2 the mass of velocity in picture 2 squared. We're good so far. The ball in picture 3 now is going to go up. And picture 3 is taken just when the ball is at its maximum height. So just when it hits that peak in its upward trajectory. Now, it's changing directions here, so that tells me it's got to be true that its velocity is 0, because it's going from a positive velocity to a negative velocity. Between positive and negative, you've got to be 0. V is 0, therefore my kinetic energy has to be 0. What about the gravitational potential energy? Well, if we're saying the ball has risen to a height h, then my gravitational potential energy is going to be mgh. If we look at the spring potential energy, again, the spring is no longer compressed, so the spring potential energy is going to be 0. If I add all three of these up, we just get that the total energy in picture 3 is the mass times g times the height that the ball is at, because it doesn't have any kinetic energy, it doesn't have any elastic potential energy. The spring is not compressed. So I get 3 seemingly different energies in the 3 different pictures. Here, I have negative gravitational potential energy because we're actually lower than the ground is. I have spring potential energy because the spring is compressed. But we're not moving, so we don't have kinetic energy. In picture 2, we are moving, so we do have kinetic energy. We have 0 spring potential energy because the spring is not compressed. But we also do not have gravitational potential energy because the ball is just at the same height that the ground is. Picture 3, the ball is not moving, it's at that peak in the air where its velocity is 0, so kinetic energy is 0. Gravitational potential energy is as big as it's going to be because it's the highest point that the ball is at. Spring potential energy is 0 because the spring is not compressed or stretched, which means the total energy is just the gravitational potential energy. We can see now that if energy is conserved, it must be true that the energy from picture 1 has got to be the same as the energy in picture 2, and the energy in picture 2 is going to be the same as the energy in picture 3, which means that 1 is equal to 2, and that's both of those have got to be the same as the energy in picture 3. Now, suppose we want to do a problem with this information. We already know, just by making the chart of the different energies in each of the 3 pictures, that my total energy has to be the initial energy from picture 1, which was some negative gravitational potential energy, plus some spring potential energy. That's got to equal the kinetic energy that we get in picture 2, because it's the total energy, is just kinetic. and it's got to equal the gravitational potential energy of picture 3. Again, because the total energy in this case is just gravitational potential energy. So suppose I want you to find the velocity in picture 2, and suppose I want you to find the height from picture 3. How would you do that? Let's give you some numbers to play with. You've got 100 joules per meter squared for the stiffness of the spring. The original compression of the spring, we'll say that's half a meter. And we'll say that the mass that of the ball that you're putting on the spring is 1.0 kilograms. Okay, so these are the parameters we're working with. From these parameters, we can find the initial energy. So I know my mass, we just said that was 1 kilogram. G, I know, is 9.8 meters per second squared. X, I'll do it down here, is half a meter. Again, half a meter over here as well. And the K was 100 joules per meter squared. So we can calculate what our total energy is. Total energy, plugging in those numbers, is just going to be 7.6 joules. Now that I know the total energy from this picture, I can figure out what V2 and the height that it goes to are. I can figure out how fast it comes off, and I can figure out how high it's going to rise up because energy is conserved. So, simplifying things, I know that my total energy, which is just this, has got to equal 1/2 mv2 squared. Okay. Well, I know the mass. The only thing I don't know is V2. But I can solve this equation algebraically for that velocity, and when you do, you'll get that V2 is equal to 2 times the energy, total energy, divided by the mass, and then we have to take the square root. Now when we do that, we should get a velocity. Again, we're just plugging in this energy, and then the mass, which was given in the problem. We should get that the ball is traveling upward with a speed of 3.9 meters per second. Okay. Easy enough, very easy to do this if we have conservation of energy and we use those principles to just calculate what the velocity is. Let's see if we can figure out what the height in this picture is going to be. I'll put down my velocity here. V2 is 3.9 meters per second. Let us now do the same thing. Again, let's simplify a little bit. Let's get rid of this guy because now I want to look at the picture where our total energy is just gravitational potential energy. So it's just how high did the ball rise up. Same thing, I know what my mass is, I know what G is. I know G is 9.8 meters per second squared. So we're just going to plug in. We're going to solve for the height. I get the height by dividing by mg on both sides. That will be E total divided by mg. And when you plug in numbers for the height, you will find that the height that the ball rises to is about 0.78 meters. So I'll put in 0.78 meters. So this is generally how conservation of energy problems work. I look at the system at one time, then I look at it at some later times. I know the total energy is in this picture has got to be the same as the total energy in that picture, and it's got to be the same as the total energy in picture 3. And since that's the same, because energy is conserved, I can use that to solve for other quantities. I can use it to find the velocity in this case, and I can use it to find the height in that case. Now I want to talk about a different type of energy. In this case, chemical energy. So chemicals store energy in the chemical bonds that they have. And if you have a certain amount of matter, a certain amount of mass of some chemical, you'll get a certain amount of energy out. So if we were to take some standard examples, let's deal with biological examples first. Let's say you look at fat. So you eat some fatty food, and it turns out you get 9 calories, food calories per gram. Now, just as a side note, I will say that a food calorie, usually you write a food calorie with a capital C. That actually equals 1,000 calories in the chemistry sense of the word calorie. So this is a food calorie. It's actually equal to a kilocalorie. In the chemical sense, just so you don't get confused. If you try to do conversions with the chemistry unit of calorie, you're going to get a number that's about 1,000 times off. But a fat is 9 food calories per gram, and if we converted that to SI units, we'd get 37 megajoules per kilogram. What does this tell us? The calorie really is just a type of energy, in the same way that a joule is a type of energy. It's just the unit that we're measuring with. Now let's say we go to carbohydrates. Okay, so you eat some pasta. Well, carbohydrates are less than half as much dense in energy as fat is. So fat is about 9 calories per gram, carbohydrates about 4 calories per gram. And that gets you about 17 megajoules for every kilogram of carbohydrate that you eat. Protein is about the same as a carbohydrate, again, 4 calories per gram, and 17 megajoules per kilogram. Now that's not the only chemicals that we're used to working with. We also have diesel, oil, gasoline, those kinds of chemicals. They have a bit more energy content, so they're about 48 megajoules per kilogram, so about 3 times what you'd get out of a carbohydrate, and about 50% more than you would get out of, 33% more than you'd get out of fat. So this is why we run our, one of the reasons why we run our cars on some sort of gasoline or oil or diesel, as opposed to fat or carbohydrates, which our bodies run on. I also put hydrogen down here. So hydrogen is a component of rocket fuel. You can also have hydrogen-powered cars. What you do in that case is you burn the hydrogen and you get liquid water out. And if you do that, you get a pretty substantial amount of energy. You get about 142 megajoules per kilogram, so almost 10 times as much as you do for protein or carbohydrates. So if we're interested in how much chemical energy our car or our bodies are using, we can use these energy densities to figure out exactly how much energy we're going to use for a given amount of fuel. So here's an example dealing with chemical energy. Call this one of the many Aaron Santos diet plans. And in fact, it involves no dieting at all. All you have to do is climb a bunch of stairs and then you can lose 10 pounds of fat. So how many stairs would you have to climb to lose 10 pounds of fat? Well, we can figure that out just by noting that 10 pounds of fat is the same as 4.5 kilograms. So 10 pounds, just doing the conversion between pounds and kilograms, we'll get about 4.5 kilograms of fat that we're trying to lose. And again, just like we did before, we're going to consider 2 pictures. Here's me with some excess weight, so that'll be about 10 pounds of weight. Then by the time I get to the top step, I've lost that weight, so I'm significantly lighter. And I want to know how many stairs I have to climb to do that. Well, recall that we have these chemical energy densities. And for fat, I will call little u, that little script u, I'll call that the chemical density of fat. And if I can find it here, we said that that was 37 megajoules for every kilogram. So I have to waste many megajoules, many joules of energy in order to burn that energy off, to eliminate the fat. We're going to look at our chemical potential energy. And to get potential energy out of this chemical energy density, I'm going to take that energy density and I just have to multiply by the mass to cancel out the kilograms. Okay, so this is going to tell me how much energy I need to lose. But let's think for a minute. I've got two pictures here. One times two. And just like we did before, let's just make a chart of the different types of energy we have. So in picture one, what we have is we're starting off on the ground. So we have some chemical potential energy that we're trying to get rid of. And we're going to try to convert that chemical potential energy to gravitational potential energy. Because as we go up the stairs, we're increasing our gravitational potential energy. To do that, we're using up chemical potential energy. So I'll call this, let me just call this UC for chemical potential energy. And initially, I have U times the mass of the chemical. In this case, the mass of the fat. So I'll call that MF for the mass of the fat. But I'm on the bottom floor, so I don't have any gravitational potential energy. If I look at my total energy, in that first picture, it's just that chemical potential energy. So it's just going to be the chemical density, the chemical energy density of fat times the mass of the fat. In picture two, I have lost that chemical potential energy. So I've lost that amount of fat. And instead, I have given my body gravitational potential energy. So that's just going to be the mass of my body. So different masses here. This is just the mass of the fat that I'm losing. This is the mass of the fat of my body times G times H. In total, I have 0 plus mgh. So in picture two, when you're at the top of the steps, you just have gravitational potential energy. I know from this that these two energies have to be equal to each other because energy is conserved. So I can say that U times the mass of the fat has to equal the mass of my body times G, gravitational constant, times H. I can solve for H. H would be U times the mass of the fat divided by the mass of my body divided by G. And when I do that, I can plug numbers in. So I can plug in the chemical energy density for fat. It's 37 megajoules per kilogram. I can plug in the mass of fat that I want to lose. That's 4.5 kilograms. That'll give me the total energy I have to use. I can plug in my body weight, which in this case, I said the mass of me is about 80 kilograms. About 180 pounds, assuming I did my conversions correctly. Then I can plug in 9.8 meters per second squared for G. And when I do that, I will get the height in stairs that I have to climb, which is about, in this case, I got 210 kilometers of stairs. So let's put that in context. How big is 210 kilometers? Well, Mount Everest is about 10 kilometers. So this would be the equivalent of climbing Mount Everest 20 times. So if you climb Mount Everest 20 times, you will be guaranteed to lose 10 pounds of fat. So it turns out it's even better than that. If you do climb Mount Everest even once, you're going to lose a significant amount of weight. Why is that? Well, the reason is that our body is not particularly efficient when it comes to converting chemical energy into useful energy of work. So converting, a lot of the energy gets lost to thermal energy, a lot of it gets lost to extraneous motions. We're really only about 20% efficient in actually converting chemical energy into useful work. So what does that mean? We said that if we take our chemical energy times the mass of fat that we want to lose, and convert that into gravitational potential energy, it would take climbing Everest 20 times. We'd have to solve and get h is about 210 kilometers. But it turns out it's a little bit better than that, because the energy that actually goes into propelling us upward along Mount Everest is only about 20% efficient. So our bodies are about 20% efficient. What that means is 80%, our bodies are 20% efficient. What that means is that 80% of the energy that we use in order to build us up, in order to move us up the mountain, 80% of that is completely wasted in terms of heat and other forms of energy. So our bodies are somewhat inefficient in that way. But that means only 20% of this chemical energy, or about 1/5, goes into moving our body up the mountain. If that's the case, I only have to go 1/5 the height that I would have. So instead of 20 Mount Everest, we'd only have to do about 1/5 of that. So you really only need to climb Mount Everest about 4 times, and you'd lose about 10 pounds of fat, guaranteed, just because of conservation of energy. Because the chemical energy I have is getting converted into the gravitational potential energy. It's only doing that at about a 20% efficiency rating, so I don't have to go up as high.